All right, ladies and gentlemen, welcome back to AP Chemistry with Mr. Kenton. If I had thought about it, I'd be playing some epic background music because we are reaching the end of Unit 1. Doesn't feel like we should be reaching the end of Unit 1, but here we are. We're in the last topic that makes up Unit 1, which is going to focus in on valence electrons and ionic compounds. And so just kind of as a pause here before I move into the bulk of our lesson, just want to kind of put us in a position of, first, do we understand valence electrons? Hopefully we do. Remember, these are the electrons that are in the outermost energy level. And if you start thinking about electron configurations as a whole, these are going to be the electrons that have the highest principal quantum number. So that's that number that comes in front of the SP, D, or F designation. So valence electrons and how those relate to ionic compounds. And if you remember from Honors Chem, the definition we looked at would have been metals and nonmetals. And for us, we have to be more specific because ionic compounds could contain or really contain cations and anions, okay? And so having that as a backdrop is going to be extremely important as we move forward and analyze this particular topic within AP Chemistry. So if you guys are ready, let's wrap this thing up. So, ionic compounds. First thing we want to think about, what happens in an ionic bond? Now, as you think about that question, hopefully your mind goes back to the fact that electrons are going to be transferred from the metal or the substance that's going to become a cation to the anion, the substance that's going to be gaining electrons here. So there is a transfer of electrons between two substances, typically from your metal to your nonmetal, but most definitely from your cation to your anion. Now, when we start thinking about ionic bonds, the ability of an atom to form bonds with another atom is going to be determined by the interactions between the valence electrons and the nuclei of the elements. So the valence electrons are extremely important because those are the electrons that experience the least Coulombic attractions within metals and also the strongest attractions within our nonmetals. Okay. Now, something that we need to consider, why do elements in the same compound tend to form analogous compounds? So compounds with the same ratio of atoms. Hopefully, as we move forward, we'll be able to address those questions, but just as a hint, it has to do with their electron configurations and the charges that their ions form. And lastly, as we look at this particular topic, is there going to be a way for us to predict or know what charges an atom is going to most likely be? The answer to that question is yes. So let's take a look at how we'd be able to answer some of these questions. So I want us to start by putting ourselves back into electron configurations. And we're going to look at it from the perspective of cations first, and then we're going to look at anions. And so if you recall, when we were doing electron configuration for something like sodium, we came up with the noble gas configuration. It's bracket neon 3s1. Well, when sodium forms a cation, it forms Na1 plus ion, which means it has the electron configuration of neon. Now, just kind of as a note, typically we don't write bracket neon for something that's an ion. We would have to write bracket helium and then write the rest of the configuration, 2s2, 2p6. Hope that makes sense. Now, for something like calcium, it's bracket argon 4s2. Well, for calcium, when it forms a cation, it typically forms a 2 plus ion, so it loses those two 4s electrons. For aluminum, bracket Ne 3s2 3p1. Aluminum most commonly forms a 3 plus charge, so it loses the two 3s electrons and the one 3p electron. Now in all of that, we should be noticing a very specific pattern. Our metals are going to lose electrons so that the cation can achieve a noble gas outer electron configuration, right? That should make sense because in all of those that we just looked at, they went to specific noble gases. Sodium and aluminum went to neon, calcium went to argon for its configuration. It's not actually argon. It didn't lose protons in these particular processes. Now we got hydrogen, it's 1s1. Hydrogen's kind of unique. It can either gain or lose electrons, but please keep in mind, hydrogen's a nonmetal. We'll revisit this last bullet. I don't want to go there yet because that term, we'll need to revisit that once we look at anions, okay? So we can see for hydrogen, it can go to 1s2 or helium. So once it gains an electron, it goes to that 1- charge. Fluorine, for example, 1s2, 2s2, 2p5. When it forms an anion, it goes to F1-, goes to 1s2, 2s2, 2p6. For something like oxygen, 1s2, 2s2, 2p4. Its most common charge or ion is the O2- ion. It goes to 1s2, 2s2, 2p6. Now for both of those, like for hydrogen, we added an electron to that 1s orbital. For fluorine and oxygen, we ended up adding electrons to the 2p sublevel within those electron configurations to form those particular ions. And then there's nitrogen, 1s2, 2s2, 2p3. It commonly forms the N3- anion, nitride, and so it goes to 1s2, 2s2, 2p6. Again, what you should see as a pattern here is that your nonmetals, they're going to gain electrons so that that anion matches up with having a noble gas outer electron configuration. Now, to our bottom bullet or bottom note here, notice that sodium ion, aluminum ion, fluoride, oxide, and nitride all have the same exact electron configuration. Now, when you run into these scenarios where you have ions that have the same electron configuration as another element, we would then say that those ions are isoelectronic, iso meaning same, electronic referring to that electron configuration, with, in this case, neon. So each of those ions there, we would say are isoelectronic with the atom neon, because they have the same electron configuration. I hope that makes sense. Now, I do want to take a moment to talk about our transition metals and other metal cations, because what we saw on the previous slide is that electrons were being removed from those orbitals, but we didn't have any d orbitals that we could interact with. Now, when you start to look at your transition metals and some of your later p block metals, like tin and lead, the electrons are going to be removed in the following order. So, Np, Ns, N-1d orbitals. Now, Np and N here, Ns, N-1, those correspond to those principal quantum numbers, right? So you're always going to remove from the p orbital first. If there are no p orbital electrons to remove from that are in the highest energy level, then we move to the s orbital. If there are no more electrons to remove from the highest s orbital, then we remove into the highest available d orbitals. Now, hopefully, as we look at some examples, that'll make a lot more sense. So, let's take a look at something like iron. So we've got iron as 4s2, 3d6. Now, one ion of iron is going to be the 2+ ion. So if we're looking at this particular kind of pattern, if we're going to form iron 2+, where's the first place we're going to be removing electrons from? Hopefully, as you've thought about that question, you'd be able to answer that we're going to remove those electrons from the s orbital first. So when we look at the electron configuration for Fe2+, it's going to be bracket argon 3d6. Again, we removed the electrons from the 4s orbital first. Now notice here, we didn't go into any of the p orbitals for iron. We didn't go back to the 3p sublevel to remove electrons there. We look at the highest energy level first, and 4s, 4 is iron's highest. Now, iron forms another cation, the iron 3+ ion. Now, since we've already seen the 2 plus ion, it should be pretty straightforward what we're going to do. We didn't have to remove any from P. We already removed all of our electrons from S. So what we're going to do next is we're going to remove an electron to form the 3 plus ion from that 3d orbital. So Fe3 plus, its electron configuration would be bracket argon 3d5. So that would be the electron configuration for iron 3 ion. Hopefully you've seen that comparison. That makes sense. Now, vanadium, for example. Okay, vanadium's got several different charges that it can form. The first one that we should be able to notice should be the 2 plus charge. So remove the electrons from the 2s sublevel. Oh man, it's getting ahead of ourselves. I wanted to keep going with vanadium, but apparently we're looking at arsenic. So with arsenic, it can form a +3 charge. So what happens there, arsenic loses those 3 electrons from its highest occupied p orbital first. Right, so notice we had 4p3 to go to +3, we removed it from the 4p orbital. Arsenic could form a +5 orbital. That would mean we would remove it from the 4s orbital. So then we'd be left with bracket argon 3d10. Now, arsenic is unique because it's a metalloid, so it can also form a negative charge. And so in this particular case, arsenide, we'd add 3 electrons to the 4p sublevel. Hopefully we're going back to vanadium here. No, manganese, what in the world? Alright, well, I digress. So manganese, argon 4s2 3d5. So if we wanted to form the anion or the cations for manganese, we should have one that's going to be, okay, this is just confusing. I'm sorry, ladies and gentlemen. I'll make this work. Alright, so we're looking at vanadium. So we go to the vanadium 2 plus. Vanadium 2 plus, we lose the 4s electrons, so then we're left with argon 3d3. Vanadium can also form a +5 charge, which means we remove all of the electrons from that 3d orbital, leaving us with just bracket argon. Alright, for copper, goes to copper 1 plus, you remove that 1 electron. Notice here, copper is an anomaly. Remember, got to remember 3 of them. Copper, silver, and I'm forgetting one. You guys are going to have to remind me later. Copper, silver, and I think it's chromium. You'll have to check me on that one. Chromium, copper, and silver. But copper loses that 1 electron. It could form a 2 plus charge, and so then it goes to 3d9 because we moved an electron from the 3d sublevel. Looking at lead, lead can form a 2 plus charge. We remove from that 6p sublevel. Or lead can form a 4 plus charge where we remove electrons from the 6s sublevel. Alright, manganese, got the 2 plus charge, removing the 2 electrons from the s sublevel. And if it's 7 plus, you're moving the remaining electrons from the d sublevel. But notice that in all of these cations, and the 1 anion with arsenic, we always followed this pattern. Remove from P, remove from S, remove from D. And you're always removing from the highest energy P, S, and D sublevels. Hope that makes sense. Sorry for all the confusion there. That even threw me for a loop. The animation. Probably should fix that. Now, the last thing we need to look at, what are these relationships on the periodic table? Are there some general patterns that we can find and that we can predict, that we could just memorize that would help us out? Now, what we see, group 1, the alkali metals, they typically form a +1 charge because they have that S1 ending in their electron configuration. For the alkaline earth metals, they're going to be +2. For the group with vanadium, those elements are going to form 2 charges, +2 and +5. For manganese, elements in that column are going to form +2, +7. For iron, the elements in that column, +2 and +3. Should have noticed that over here, when we were in the 4A or the 14, they form +2, +4 charges. And then as we shift over to the nonmetals, notice that the charges are now negative. So nitrogen, phosphorus, and arsenic, -3. in the chalcogen family with oxygen, sulfur, selenium, tellurium, going to form a -2 charge. Elements that are in group 3A, +3. And then for our halogens, they always form a -1 charge. Now hopefully we can understand from their electron configurations why that's the case. Now with that, ladies and gentlemen, we have ended Unit 1. We are at the end. We just talked about valence electrons and ionic compounds. I hope this was a useful video to you. Please make sure you go through, complete the Google form after watching this. Let me know any questions that you have, any concerns. Let me know your comfort level with this. And I look forward to seeing you guys again soon. Take care, and I'll see you guys next time.